So for this final session, before the afternoon tea in Science and Data, we've got Byron Allen, and he's going to be talking about tracking land conversion with the eye in the sky. Thanks, Byron.
Thank you. Thank you, everybody, for coming and hearing me speak. So I am a data consultant. I work for a company called Servian, based in Sydney, and we have offices around Australia. But so that means my day-to-day job is kind of more on the data engineering side of things. But I, in my spare time, I play around with satellite images. And this particular talk spawns from a data science course that I took at General Assembly. So I was doing their boot camp, and as a part of that, you have a final project. And that's where this talk started. But it's kind of evolved into something a little bit beyond what I initially did, and I kind of want to talk about that today. So land conversion. When I say land conversion, I'm going to talk about it in a more specific context, and I want to go through what that is and why I think everybody should be aware of it. Then I'm going to talk about satellite images, how you might go about acquiring them, and the tools that you might be using to manipulate them. The next thing is a little bit of context to understand my specific topic. There's definitely some things you need to know, otherwise it might be kind of hard to follow what I'm saying. Then the last two parts of the presentation will be about my first project and the failings of that first project and what I went, or how I went about improving it. So land conversion. What do I mean when I say land conversion? I think everybody's heard of deforestation, and this image is from the Amazon. Probably relatively familiar to everybody. I know it's very familiar to me. I learned about deforestation when I was in 3rd grade. Our class did this little project where we did like a papier-mâché rainforest, and we wrote a letter to President Bill Clinton asking him to help stop deforestation. And from that point on, it really stuck in my mind, and I always kind of had this, this idea of conservation as being something I wanted to be a part of. And fast forward 15 years, and I'm doing this data analysis project around the Renewable Fuel Standard. Now, the Renewable Fuel Standard is a piece of legislation in the United States that requires refiners to add X amount of biofuels into their gasoline at an increasing rate each year. Now, this has questionable ecological and economical impacts. And as you can probably tell, corn is the predominant source for those biofuels in the United States. And so that's where cropland comes in. And that's why I was interested in land conversion, because, okay, well, if we're going to go from wildlands, whether it's grassland or forests, and convert them into cropland, how might that impact climate change, the ecology in general? And the one thing that I found very frustrating in that analytics project was that there's a severe limit on the amount of data that I could get. There was only 1 year of publicly available data that spoke to land conversion in the United States, which was ultimately very disappointing at the time. But I realized it might actually be an opportunity. So when it came to the final project in my General Assembly data science course, I realized this might actually be an opportunity. What if I could use satellites and the machine learning methods that I was learning through the course to create a record of that land conversion, of that change from wildland to cropland? So I went about investigating, okay, how do I leverage satellites, satellite images to create this record? And the first place you're going to probably start if you're going to go down, have that conversation is, where do you acquire those images? And there are a lot of places, but I found one of the easiest was this Google Earth Engine, which is a browser-based IDE built for research. And unfortunately, it's mostly in JavaScript. But it does allow you to very conveniently and quickly define a geographic location and export the rasterized images, so like a GeoTIFF file, for example. So that was a very quick way of acquiring the satellite images that I needed for my analysis. So the next question then becomes, okay, you know where to go to acquire the data, but you have many satellites to choose from. And if you look at this space from a broader perspective, there's private satellites and there's public satellites. There's a lot of data out there to get your hands on. There are some publicly available sources, such as the Landsat series, which have been around for several decades. Landsat 8 in particular is what I use because it had the most recent years. So it was launched in 2013, and I was looking from 2013 to 2015. And so I went about using Landsat 8 data. So the one thing I had to bear in mind was Landsat 8's orbit. And this would be true with any of these satellites, is when it orbits in near-Earth orbit, and Earth will spin, which means that the satellite only covers the same piece of land roughly every 16 days. So you end up with an image of any given location, so like Melbourne, for example, will only appear in the record once or twice a month. And so I had a good sense of the frequency of the data, what kind of data I would be accessing. And then it came down to, OK, well, how do I manipulate this data? And I think probably a lot of this will be very familiar to many of you. So the typical data science stack, like Pandas, NumPy, scikit-learn, those were my go-tos. But there's also this more modern GIS stack that I think is really valuable if you're interested in exploring this space, such as Rasterio, Fiona, Shapely. In particular, I use Raster.io or Rasterio, however you want to pronounce it. I went to that, and that's a really useful way of accessing the contents of geotiff files, which is what Google Earth Engine was spitting out. So here's a few examples of Rasterio and what you could get from it. I'm opening this geotiff file, and I'm able to access the number of bands and some metadata around height, width, and other information that might be useful for my analysis. Another one would have been, and this is one that I widely use, was accessing the specific bands themselves. So you would say if you needed to access your blue, red, green, or infrared, for example, you would specify it in this manner. And you could very quickly grab those layers. And then Raster.io also enables the ability to write out into geotiff, which was quite convenient. And that's really only tipping the tip of the iceberg for Raster.io. And if you really want to get started in this space, if you haven't really explored it yet, there's these 2 tutorials that I started messing around with or went through when I was getting into the space, and I found them really influential. I'll put them up on the Slack channel after this. So, OK, that kind of gives you a sense of where to get the data and what tools you might be using. But what do you need to know about this my specific topic? So there's this thing called center pivot irrigation. And it's a way of irrigating cropland where it's this boom that pivots from a central point and waters the land. What that does is that creates these kind of crop circles. So it's an easy way of identifying cropland. As you can tell, there's these little green circles everywhere, dotted throughout the landscape. So it throws some people off when they see that for the first time because they don't know what they're looking at. But it's something to bear in mind. And another thing that will be helpful in terms of providing context is Landsat 8 provides a series of multiple frequencies in the electromagnetic spectrum. But for when you're looking at vegetation, there's 3 in particular that are going to be really useful. So your blues, your reds, and your near-infrared. And together, those would be combined and pushed through this algorithm, this enhanced vegetation index algorithm. And the output is very useful in identifying vegetation. So not specifically cropland, but if you look at that image, you start to see those circles again in bright pink, which is to say that they're showing up very prominently in this image. So, but when you get that enhanced vegetation index, really what you're looking at is it's unlabeled data. So that would lend itself towards an unsupervised method. You would want to cluster or label or ultimately infer groups. You would want to be able to say, is this pixel cropland or is it something else? Is it vegetation? Is it forest? Is it desert, et cetera? And so for me, I chose k-means. And it is probably one of the more simple clustering methods to understand. one of the more simple ones to implement. It scales well with large data, and it labels all your rows. So unlike algorithms, say like dbScan, which might drop some of your outliers, this will label every single row in your data set. So that was one of my starting points. And that kind of brings me to the first method that I took in approaching this problem of trying to identify and track land conversion. So I took that EVI, that Enhanced Vegetation Index, and I started looking at the distribution of that data. And what I often saw, especially in an image where it was a mixture of cropland and non-cropland, is this bimodal distribution. And I noticed that if you look at that right distribution, you can kind of crop that off and you get this impression of cropland. Now that's really simple. That's not particularly a sophisticated way of identifying cropland, but I noticed that and I kind of cut that and kept it to the side, and I called that my agriculture mask. The next thing I did was I tried to go about creating my own vegetation index, which is, it was a good effort, but I think in retrospect, EVI is still very strong at identifying vegetation. So in any case, I went ahead with my vegetation index, clustered on that, and then I would overlay my mask with those clusters to kind of do a cross-check and then consolidate those labels to identify cropland and non-cropland. So I did this for a piece of land in Nebraska, which I knew to be, as a state in the United States, it had the highest amount of land conversion in 2011, so it was a good place to start. And so I took this piece of land, I took a raster image of it. This is what it would look like in natural color. And then when I put it through my method, it would come out like this. And you would have cropland in orange, unsure in blue, and then non-cropland in green, which is really quite, it was good, and it made me really happy when I first saw this, but it was still, it seems somehow very simple. I could tell that there was sort of this dip in non-cropland over this 2013 to 2015 period, and there's a little bit of a rise in cropland, but it kind of leveled out, and there's this unsure element. So it really raised the question, how do I deal with this unsure element? How do I deal with this unknown? And I realized there's two ways of going about this problem, is to do a better job at capturing the nuances and the different types of landscape that you have, or use some kind of a probabilistic model. So I've heard of, in carbon accounting, a model that is probabilistic, but that works for carbon accounting because if you're looking at the EVI, this Enhanced Vegetation Index, you have something on one extreme, it's very binary. So you have vegetation or it's not. And that's what you're looking at when you're looking at carbon accounting. But if you're trying to identify cropland versus non-cropland, it's a bit more nuanced. So in trying to improve my model, I sought this method of trying to identify different types of land cover. So I realized I needed to increase the number of data sets that I was, or samples that I was actually taking, because I was only taking a sample from the peak growing month of each year. So one of the core tenets of this improved model that I've tried to work on was taking a sample from each month, and then off the back of those 12 months, well, first off, in those 12 months, you can kind of see that from month to month, it changes. Agriculture changes. Cropland disappears because it grows and it gets harvested. And so doing feature engineering off the back of those 12 months could be really valuable in understanding where cropland is. And you can see on the left, there's annual standard deviation. It's quite, you can see the cropland is quite prominent in that image. And that's not actually a direct image, that's standard deviation. When I first saw that, I was really thrilled because what that means is you're capturing that nuance across 12 months. So to me, it felt like, okay, I'm on the right track. So what I did was I continued to do feature engineering, and I created a total of 67 features for my data set. Taking means and sums and standard deviation, variation, differences from this month, this quarter, and just trying to get as many features as I could. I then took that data set and spun it through a morphology algorithm, which effectively smooths the algorithm. So sort of like smoothing time series data, if you will. It's like a rolling average, but for images. And you can see that on the left, in the left image, it's kind of splotchy and it's a little bit unclear. But in the right image that has morphology applied to it, it's a little bit more clear. It's a little bit easier to understand. So when you go for a visual inspection of the data, which you'll do a lot because you're handling images, it's a little bit more clear. So going back to k-means, so I have my morphed 67 feature data set. And with k-means, you have to figure out, OK, what's the ideal number of clusters? And this becomes one way of approaching this is using silhouette scores, which you see on the left. And your ideal silhouette score is 1. And you can see that there are some number of clusters where the ideal silhouette score is maybe closer towards like 6 clusters. And then on the right-hand side, you can see it's like 26 clusters. And there's a very high silhouette score. But the issue is too few clusters, and you don't capture that nuance. It's going to be harder for me to get to the different topology that I'm after. Too many clusters, and I'm just going to get lost in clusters. And I'm going to have a hard time discerning what's what. So I tried to find a middle ground, which is why you see that annotation around between 11 and 14. So once I took my new feature set and applied it through that method and found my number of clusters that I wanted to use, this is what a data set would come out like. And what I'm really doing here is trying to go for a ground truth. And you can see that there's a far greater amount of nuance than that first graph that I showed you. You can see that there's crop and orange spotted throughout. You can see different types of vegetation throughout the map. And then there's this final one, which I thought was really quite interesting, where it's actually vegetation along the river. And you can see that it's helping to identify where the river is to a large extent, which I think that was really promising from my perspective, because it said, OK, you're starting to get to a point where you're capturing a greater amount of nuance. And all of this really goes to a ground truth. You want to be able to identify your ground truth, what is actually there, because we're trying to put labels on nature. And nature is not exactly well defined. When does a forest end and when does it begin? So did I find the best ground truth method? I hope so. And one of the ways I went around testing that ground truth method is taking it from Nebraska to Florida to this area, where in green you see a lot of wetland right next to cropland. So you start to see there is this difference, even though both have a lot of vegetation, you can certainly discern the difference between the two of them. So I'm finally getting to a stronger ground truth. And that's really important because the next step of this entire thing is you can't keep building this ground truth on it for every single location that you find. If you wanted to, say, do a map of Victoria in this way, you would be leveraging a lot of data, and it would be quite time-consuming. But the ideal solution to get to is to go from this ground truth and use that ground truth to build a supervised model. And then you can start to spit anything through a supervised model and predict the outcome. So am I done only with this presentation? But hopefully not with this project. So thank you.
Thank you very much, Byron. And again, a gift as a token of our appreciation.
Thank you.
Do you have any questions?
We noticed that you use like a number of features. Would you be able to share further on how you arrived on getting the features, and how did you do your feature engineering side?
Yeah. So I can go back to it. So for example, if you look at all the standard deviation ones, so STD, I just took it from each quarter, did it for the entire year, did it for a summer period, for half a year. I think with feature engineering, the thing is, if you're really doing that, you don't know where you're going with it. you don't know what feature is going to be good and useful, so you just keep engineering as many features as you can. And you do it as you create a data set as wide as you can, and hopefully something sticks.
Yeah, here in Australia, there was a project to create something called I think it's the Geoscience Data Cube, where they did have, they made Landsat data available, and they also tried to predict that you'd want to analyze it over time, so you could do time series analysis. But it looked like from your talk, were you kind of happy to just get rasters from something and then do all your own post-processing, or did that sort of work for you? Any comments on that?
So, I mean, I guess what I did was this initial data discovery phase, and I haven't productionized this at all. I think that's something I would be building up to, because I would love to do that if I could, and cover other topics besides, say, land conversion. So land conversion is kind of close to my heart because I'm a bit of an environmentalist, but there's a lot of other issues out there that you could apply this method in a very similar way. Does that quite answer your question?
I guess because you didn't. I'm trying to get at. Did you? What sort of main data representations did you work with? I saw you had a data frame at one stage, one of your images. So was it mainly you didn't do a lot with the rasters themselves? You got things into pandas
right.
or something
Okay,
like that?
I see what you mean. Yeah. So I was really just taking rasterized images and then putting them into NumPy, because I think that was the most convenient and easy way for me to do that at the time. I think that's the way I would continue to go forward with it, is open those raster images up and then go forward. One thing though, you can use raster.io to say, take that image, like this one for example, and then pump it back out, and you could put this into a similar format where you could apply metadata for other proper mapping.
What's next? Do you have any plans for the probabilistic programming you mentioned on tracking uncertainty, or what are your plans?
I guess that's, yeah. So the thing is to start applying this to different regions and different areas where I know it's not the same type of topology as, say, that area in Nebraska. I want to check other areas. And then you build up those land type classifications. And then I think the idea would be to combine them into a training set, and then move on to developing some sort of supervised method.
Cool. Can I have a follow-up? On a separate note, were you using time series data for a couple of years at every 16-day interval to create all your features?
No, I was taking one sample from each month, because I wanted something to represent each month.
Okay. So with that, do you just get one sample in summer, or just a few? The 3 or 4 months that happen to be in each season. So do you see seasonal effects particularly well for crops?
I think that's kind of what I'm banking on in creating those engineered features, is that there will be those changes, and that in doing feature engineering that captures those changes, you can create a model that's more informed.
Okay. Thanks.
Maybe I just missed your explanation, but when you were actually clustering, my understanding is that actually clustering of the different values of the intensity of the EVI values you were getting from the data. Is that what you were doing, just to quantize the intensity values? Is that right?
Correct. Yeah.
Okay. And then the other question is, I think we actually were wondering here with my colleague, when you actually were selecting the features, you did it by hand, or you actually just ran some algorithm to select the features based on some criteria?
When you say select the features?
The features, like you had all the different variances and...
Yeah, so I built it out, and you mean some sort of feature reduction?
Yeah, but you actually just use some
That's one thing I've thought about exploring a bit more, using a principal component analysis to reduce the feature set. At the moment, I haven't really reduced it.
So it's just handpicked?
Yeah,
okay,
it's just that wide data set.
Thank you.
G'day, mate. Just a pretty simple question. How do you deal with cloud coverage when you run these satellite photos too?
Yeah, that's a good one. I think I've kind of resigned myself to accepting that it's going to be there, and you have to work around it to some extent. And I think there's value in taking 12, like a sample from each month, in that you kind of reduce the impact of clouds. But yeah, it's a little bit unavoidable to some extent. You can't like remove clouds completely. You just have to bear that in mind. And so I'm building ground truths. I think it's ideal that I pick areas where there's minimal cloud coverage throughout my samples. That's basically what I've done. Yeah.
Thank you. Nice talk. To build your time series, how did you line up the pixels from one month to the next to know that you were looking at exactly the same bit of ground each time?
Yeah, so basically what you end up doing is you flatten the array. So you would take these images and you would flatten them out. So if you think about it in terms of like columns, you would have 12 columns, one for each month. And then your pixels are indexed to the index. So each pixel has an equivalent.
Okay, are there any further questions? Otherwise, I think it's time for afternoon tea. Can we please give a big round of applause to Byron again? Thank you very much.